The IAEI, or International Association of Electrical Inspectors Southern Sectional meeting is an event where electrical professionals gather to discuss the latest updates, interpretations, and applications of electrical codes and standards. These meetings provide a valuable opportunity for inspectors, contractors, engineers, manufacturers, and other industry stakeholders to network, share knowledge, and enhance their understanding of safe electrical practices. Attending such a meeting offers numerous benefits. Firstly, code updates. These meetings often feature presentations and discussions on the latest changes and revisions to the National Electrical Code, or NEC, and other relevant standards. This information is crucial for staying current with industry best practices and ensuring compliance with regulations. Secondly, continuing education. Many IAEI sectional meetings offer continuing education credits, or CEUs, which are often required for maintaining professional licenses and certifications. These sessions cover a wide range of topics related to electrical safety, installation, and inspection. Thirdly, networking opportunities. These meetings provide a platform for connecting with other professionals in the electrical industry. Networking can lead to valuable collaborations, mentorship opportunities, and insights into different perspectives on electrical issues. Fourthly, technical knowledge enhancement. Presentations and workshops at the meeting delve into specific technical aspects of electrical systems, offering attendees the chance to deepen their understanding of complex topics. This can include discussions on grounding and bonding, overcurrent protection, wiring methods, and more. Fifthly, code interpretation. IAEI meetings often include sessions dedicated to clarifying interpretations of the NEC and other codes. These discussions can help resolve ambiguities and ensure consistent application of the code in different jurisdictions. Sixthly, product demonstrations. Manufacturers often showcase their latest products and technologies at these meetings. Attendees can learn about new innovations in electrical equipment and materials, as well as their proper installation and use. Seventhly, problem solving. The meetings provide a forum for addressing specific challenges and questions related to electrical installations. Attendees can share their experiences and seek advice from other experts in the field. Eighthly, safety promotion. A primary focus of IAEI is promoting electrical safety. The meetings emphasize the importance of safe electrical practices and provide resources for improving safety in homes, businesses, and industrial facilities. Ninthly, professional development. Attending IAEI sectional meetings contributes to ongoing professional development, helping individuals stay at the forefront of the electrical industry and enhance their skills and knowledge. Tenthly, industry insights. The meetings offer insights into current trends and challenges facing the electrical industry. This can include discussions on topics such as renewable energy, electric vehicle charging, and smart grid technologies. The NEC, published by the National Fire Protection Association, or NFPA, is a widely adopted standard for safe electrical installations in the United States. It is updated every 3 years to reflect new technologies, materials, and best practices. Some key aspects of the NEC include, firstly, scope and purpose. The NEC covers the installation and maintenance of electrical wiring and equipment in residential, commercial, and industrial buildings. Its purpose is to safeguard people and property from hazards arising from the use of electricity. Secondly, organization. The NEC is organized into chapters, articles, and sections. Chapters cover general requirements, wiring and protection, wiring methods and materials, equipment for general use, special occupancies, special equipment, and communication systems. Thirdly, grounding and bonding. Article 250 of the NEC provides detailed requirements for grounding and bonding electrical systems. Proper grounding and bonding are essential for minimizing the risk of electric shock and fire. Fourthly, overcurrent protection. Article 240 of the NEC covers overcurrent protection devices, such as circuit breakers and fuses. These devices are designed to protect electrical circuits from overloads and short circuits. Fifthly, wiring methods. Chapter 3 of the NEC specifies acceptable wiring methods for different types of installations. These methods include conduit, cable, and other wiring systems. Sixthly, equipment for general use. Chapter 4 of the NEC covers the installation of electrical equipment such as receptacles, switches, lighting fixtures, and appliances. Seventhly, special occupancies. Chapter 5 of the NEC addresses special occupancies such as hazardous locations, healthcare facilities, and swimming pools. These occupancies have unique electrical requirements due to their specific hazards. Eighthly, tables and examples. The NEC includes numerous tables and examples to help users apply the code correctly. These resources provide guidance on conductor sizing, overcurrent protection, and other critical aspects of electrical installations. Ninthly, enforcement. The NEC is typically enforced by local and state electrical inspectors. These inspectors review electrical plans and inspect installations to ensure compliance with the code. Tenthly, amendments. Local jurisdictions may amend the NEC to address specific needs or concerns. It is important to be aware of any local amendments when designing or installing electrical systems. Grounding and bonding are critical for electrical safety. Grounding provides a path for fault current to flow back to the source, allowing overcurrent protection devices to trip and to energize the circuit. Bonding connects non-current carrying metal parts to create a low impedance path for fault current. Some key concepts related to grounding and bonding include: firstly, grounding electrode system. The grounding electrode system consists of one or more grounding electrodes, such as ground rods, metal water pipes, or concrete encased electrodes. These electrodes are used to connect the electrical system to the earth. Secondly, equipment grounding conductor. The equipment grounding conductor, or EG, is a conductor that connects non-current carrying metal parts of equipment to the grounding electrode system. The EGC provides a path for fault current to flow back to the source. Thirdly, bonding jumpers. Bonding jumpers are used to connect different metal parts together to create a low impedance path for fault current. Bonding jumpers are commonly used to bond metal water pipes, gas pipes, and other metal objects to the grounding electrode system. Fourthly, ground fault circuit interrupters, or GFCIs. GFCIs are devices that detect ground faults and quickly to energize the circuit. GFCIs are required in locations where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor areas. Fifthly, arc fault circuit interrupters, or ARFCIs. ARFCIs are devices that detect arc faults and to energize the circuit. Arc faults are a common cause of electrical fires. ARFCIs are required in many residential circuits. Sixthly, separately derived systems. Separately derived systems, such as generators and transformers, have their own grounding requirements. These systems must be grounded in accordance with Article 250 of the NEC. Seventhly, impedance. Impedance is the total opposition to current flow in an electrical circuit. Low impedance is essential for effective grounding and bonding. Eighthly, voltage drop. Voltage drop is the decrease in voltage along a conductor due to its impedance. Excessive voltage drop can cause equipment to malfunction or overheat. Ninthly, harmonics. Harmonics are unwanted frequencies in an electrical system that can cause equipment to overheat and malfunction. Grounding and bonding can help mitigate the effects of harmonics. Tenthly, surge protection. Surge protection devices, or SPDs, protect electrical equipment from voltage surges caused by lightning or other events. SPD are typically connected to the grounding electrode system. Overcurrent protection is another essential aspect of electrical safety. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. Some key concepts related to overcurrent protection include: firstly, ampacity. Ampacity is the current carrying capacity of a conductor. The ampacity of a conductor depends on its size, material, and insulation type. Secondly, circuit breakers. Circuit breakers are overcurrent protection devices that can be reset after they trip. Circuit breakers are commonly used in residential and commercial electrical systems. Thirdly, fuses. Fuses are overcurrent protection devices that must be replaced after they blow. Fuses are available in a variety of types and sizes. Fourthly, inverse time characteristic. Overcurrent protection devices typically have an inverse time characteristic, meaning that they trip faster for higher levels of overcurrent. Fifthly, interrupting rating. The interrupting rating of an overcurrent protection device is the maximum fault current that it can safely interrupt. The interrupting rating must be high enough to handle the available fault current at the point of installation. Sixthly, selective coordination. Selective coordination is the practice of coordinating overcurrent protection devices so that the device closest to the fault trips first, minimizing the impact of the fault on the rest of the electrical system. Seventhly, series ratings. Series ratings allow the use of overcurrent protection devices with lower interrupting ratings in certain applications where they are protected by upstream devices with higher interrupting ratings. Eighthly, conductor sizing. Conductor sizing is the process of selecting conductors with sufficient ampacity to carry the expected load current. The NEC provides tables and guidelines for conductor sizing. Ninthly, transformer protection. Transformers require special overcurrent protection to protect them from overloads and short circuits. The NEC provides specific requirements for transformer protection. Tenthly, motor protection. Motors also require special overcurrent protection to protect them from overloads and short circuits. The NEC provides specific requirements for motor protection. Wiring methods and materials are also important considerations for electrical safety. The NEC specifies acceptable wiring methods for different types of installations. Some common wiring methods include firstly, rigid metal conduit. Rigid metal conduit, or RMCE, is a heavy-duty conduit that provides excellent protection for conductors. RMCE is commonly used in industrial and commercial applications. Secondly, intermediate metal conduit, or IMC. Intermediate metal conduit is a lighter weight conduit than RMCE. IMC is also commonly used in industrial and commercial applications. Thirdly, electrical metallic tubing, or IMT. Electrical metallic tubing is a thin-walled conduit that is easy to bend and install. EMT is commonly used in residential and commercial applications. Fourthly, flexible metal conduit, or FMC. Flexible metal conduit is a flexible conduit that can be used in tight spaces or where vibration is present. FMC is commonly used to connect equipment to electrical boxes. Fifthly, non-metallic conduit. Non-metallic conduit, such as PVC conduit, is a lightweight and corrosion-resistant conduit. Non-metallic conduit is commonly used in underground applications and in areas where corrosive chemicals are present. Sixthly, cable. Cable is a factory assembly of two or more conductors enclosed in a sheath. Common types of cable include non-metallic cable, or NN cable, and armored cable, or AC cable. Seventhly, conductor types. Conductors are available in a variety of materials, including copper and aluminum. Copper is a better conductor than aluminum, but it is also more expensive. Eighthly, insulation types. Conductors are insulated with a variety of materials such as PVC, XLPE, and rubber. The insulation type must be suitable for the application and the environment. Ninthly, boxes and fittings. Electrical boxes and fittings are used to enclose and protect electrical connections. Boxes and fittings must be listed and labeled for their intended use. Tenthly, wiring devices. Wiring devices, such as receptacles, switches, and dimmers, are used to control and distribute electricity. Wiring devices must be listed and labeled for their intended use. Special occupancies, such as hazardous locations, healthcare facilities, and swimming pools, have unique electrical requirements due to their specific hazards. Hazardous locations are areas where flammable gases, vapors, or dust may be present. The NEC classifies hazardous locations into different classes and divisions based on the type and concentration of the hazardous material. Healthcare facilities have stringent electrical requirements to ensure patient safety. The NEC provides specific requirements for the installation of electrical equipment in patient care areas. Swimming pools also have unique electrical requirements to protect swimmers from electric shock. The NEC requires the use of ground fault circuit interrupters, or GFCIs, for receptacles and equipment located near swimming pools. Understanding and applying the NEC correctly is crucial for ensuring electrical safety. Electrical inspectors, contractors, and engineers must stay up to date on the latest code changes and interpretations. Attending IAEI sectional meetings and participating in continuing education courses are excellent ways to enhance knowledge and skills in the electrical field. By adhering to the NEC and following best practices, electrical professionals can help prevent electrical hazards and protect people and property from the dangers of electricity.